Hello everybody, Mr. Johnston here, and we are going to talk about properties and bonding in this video. And this video should help you fill out this table or this chart that you have. And we'll go through each property and each of the types of bonding as well. And so I'll kind of work my way from top to bottom, left to right. And so we'll start with structures in ionic, and then we'll go to structure in polar covalent, and structure in nonpolar covalent, and so on. Before we get into the structure and properties, I do just want to mention that when we talk about properties a material has, it is largely due to the type of bonding within the particles. Not only that, it's also due to the intermolecular interactions between the particles that make up the material. And so it's important for chemists to be able to examine these properties and use that information to determine the type of bonding that is occurring within a material. So first, let's talk about the structure of substances. So the way that atoms and molecules arrange themselves on a microscopic level can often be observed on the macroscopic level. So if we think about ionic compounds first, ionic compounds have very orderly and repetitive arrangements of cations and anions. We call this a crystal lattice. And so one thing about ionic compounds is if we think about how sodium chloride, if you look at the image on the left there, we have a repeating pattern in 3 dimensions of sodium, chlorine, sodium, chlorine, sodium, chlorine, and so on. And if you actually zoom in on sodium chloride crystals, you would see they are nice, neat little cubes. And that's because of the 3-dimensional arrangement of the ions on the microscopic level. Also, it's worth noting here that ionic compounds are solids at room temperature. So let's talk about polar covalent compounds. These tend to be solids or liquids at room temperature because the molecules attract one another. So if we think about water, for example, it's a liquid at room temperature because one molecule of water is attracted to another molecule of water through a hydrogen bond. The same would be true for a substance like ethyl alcohol. That's the image on the bottom right. Ethyl alcohol is C2H6O, and it has a hydrogen bond between one ethyl alcohol molecule and another. Nonpolar covalent compounds, the structure really depends on the amount of London dispersion force between the molecules. In other words, it's the size of the atom or molecule that's important, because the larger the atom or molecule, the more London dispersion force there will be. So small nonpolar molecules tend to be gases at room temperature. So if you think about something like helium, helium is nonpolar. Those are just atoms. Helium is a gas at room temperature. Something like methane is also a gas at room temperature. If we get to larger alkanes, something like over here, this is hexane, and there are many atoms there and hence many electrons, and those electrons are polarizable, which means that the electron cloud can be kind of pushed and pulled around to make those temporary dipoles that attract one another. These substances, if you have a small, it's nonpolar molecule, it's going to be a gas at room temperature, while a large nonpolar molecule will be a solid at room temperature. These substances are said to be amorphous. In other words, they don't have a very rigid shape. They are more random in their shape. Metallic substances have valence electrons that can flow past from one atom to another through the sea of electrons, meaning that atoms can slide past each other when force is applied. This makes them malleable or ductile. And so if you think about like a piece of metal, if you hit it with a hammer, those atoms, they'll slide past each other a little bit, but it doesn't break necessarily, it just deforms because those atoms are attracted to the sea of electrons, which are movable. The melting points of metals tend to vary depending on the metal. We talk about ionic compounds, or let's move on to phase changes, So a phase change is when a substance melts or vaporizes, and in order to do this, you have to add energy to break the intermolecular interaction. And so something like an ionic compound have very strong interactions between oppositely charged ions. Therefore, these substances have very high melting points. You have to put a lot of energy in to get those ions to move away from each other because they're so strongly attracted to each other. If we think about polar covalent compounds, they have a relatively strong interaction between those molecules. So these substances tend to have kind of intermediate melting points. And nonpolar covalent compounds, these have relatively weak interactions between molecules. So these substances tend to have very low melting points and very low boiling points. If we think about something like carbon dioxide only becomes a solid if we get it down to negative 78 degrees Celsius. And that's also the temperature if you're have something like dry ice, that's solid carbon dioxide. It'll turn to a gaseous phase at that temperature, negative 78 degrees Celsius. Metals, on the other hand, their melting points and boiling points vary greatly from one metal to another. Generally speaking, metals tend to have high melting points, but a classic example is mercury. Mercury is a liquid at room temperature. Other metals, you have to heat them up really hot before they'll turn to a liquid. So it does vary greatly for metals. The next thing we're going to talk about is solubility. So a material's ability to dissolve in water really depends on how it interacts with polar water molecules. So ionic compounds, they do tend to be soluble in water because the ions interact with water via those ion dipole interactions. I should mention, though, there are some ionic compounds that are less soluble because the ions within the compound, they're more attracted to each other than they are to water molecules. And so in that case, they'd be less soluble. Polar covalent compounds do dissolve in water because the polar part of the molecule interacts with polar water. And so something like sugar, it's a polar compound, and it does dissolve in water. It gets surrounded by water molecules and pulls apart those sugar molecules. One thing that you should note, going back to ionic compounds, is when they dissolve, the ions separate. We call that dissociation. When polar molecules dissolve, the molecule itself stays whole, intact. And so you get one molecule totally surrounded by water molecules. Nonpolar covalent compounds do not dissolve in water because the nonpolar molecules don't have a strong attraction to polar water molecules. So oil and water, classic example, don't mix because oil is nonpolar. Metals also do not dissolve in water because the metal atoms are attracted to the sea of electrons much more so than they are attracted to water molecules. So metals do not dissolve in water. Conductivity. So conductivity is really the movement of charged particles. In order for a material to conduct electricity, there must be charged particles that are free to move. Thinking about ionic substances, in the regular solid state, ionic substances are not conductive. However, if you melt ionic substance, so if you put it in the molten state, or if you have an aqueous solution of ionic compounds, they are conductive, because in the aqueous state, these ions are dissociated and they're free to move through the solution. Similarly, if you melt an ionic compound, and you do have to get it very hot to melt it, but in that case, the ions can move around and therefore we can conduct electricity. Polar covalent compounds are not conductive in the solid state or in aqueous states, or when they're melted for that matter. When polar covalent compounds dissolve, they do not dissociate, and so there is no movement of charged particles. Nonpolar covalent compounds are not conductive in the solid state, and they do not dissolve in water, so that's not going to change anything there. Metals are conductive in the solid state because the electrons in the sea of electrons can move independently of the atoms. And so if we hook up a wire, for example, to a voltage source, we can actually get all of the electrons to move in the same direction. All of those valence electrons, I should say, can move in the same direction, and we get that movement of charged particles. That's conduction.